Hey, what's up, guys? Welcome to my YouTube channel. This video I want to talk about another application of this cyclotomic polynomial, which is called this Wedderburn theorem. Also, this theorem is interesting, and you can see the famous algebra textbook like Hurston, which give the proof. So I will use the cyclotomic polynomial to give you the very quick proof. Okay, the proof is beautiful. So this theorem says that every finite division ring is a field. Okay, so finite division ring means that you have division ring, right? So division ring is the ring which not commutative, but each element non-zero has the inverse, right? So for example, if you know the quaternion and also octonion. Okay, so these are like famous division ring. But if you have finite division ring, then this guy must be a field. Okay, so in order to prove this, we need a very simple lemma of the cyclotomic polynomial. So recall that you can find x defined to be like the product of x minus exponential 2 pi I divided by n g, where g is less than n and greater than 1, greater or equal to 1, and g is the GCD of this gn is 1. Okay, so we have a simple lemma. So if we take q to be the integer, positive integer, which greater or equal to 2, greater or equal to 2, then obviously that is phi and q will be a real number, because this guy is has the integer coefficient, and the absolute and the phi and q will be greater than q minus 1. Okay, this is what we need to use this. Okay, so yeah. Okay, so we know that this guy is positive real, right? The reason is why? The reason is that first we know it's real, and we know that if we take phi and q, right? So we have maybe using j, just more the convenient using j. So we have phi and q, right? So we know that phi and q is the product of, let's say, q minus epsilon. Let's say epsilon is just this guy's epsilon. Right, so we just a product of epsilon power, right? We have some epsilon, and then there's a Euler function by phi and of them, and then there are some different power here, and but we know that q is greater than 2, greater or equal to 2, right? So q minus epsilon, right? So epsilon is a root of unity, so maybe here, and then q is 2, right? So this distance must greater or equal to what? So greater or equal to 1, right? Bigger, and also greater or equal to q minus 1. If this is q, right? So the group must be greater. This distance is q minus 1, and so this black distance must be greater than q minus 1. Okay, so your phi and q absolute value must be greater or equal to q minus 1 times 5n. Okay, obviously greater or equal to q minus 1. Okay, so we have this and we have this. So this is one trivial because each the distance, this distance is greater or equal to this distance. Okay, so now let's go to the proof. Okay, so proof every finite division ring is a field. Okay, so proof idea is the following. The idea is let's say we consider D is a finite division ring. And then we consider K to be center. Okay, so center is just the x belongs to D, and the xy equals to yx for every y belongs to D. Okay, and we can take let's see. So obviously that right, if you can view D is the vector space over K. So D is vector space over K. Let's say you consider K as Q root, the Q, then the coordinate is Q, then the D, so D is basically Q to the N. Okay, so our goal is to show what? Our goal is to show N is 1. Because if we show N is 1, then D is K, right? But K is a field. So this guy is a field. Okay, so now okay, so the proof idea is very simple, right? We can take, let's say we take A, right, which do not belongs to the K. And we consider L, where L is the X belongs to D, where AX equals to XA. Right. So basically it's the guy which commute with A. Okay, so obviously that we have K is a subset of strictly subset, right? Because A do not belongs to K, and there is a subset in L. D, right? So this is a vector space over it, vector space over it. Okay, so obviously that L has the Q to the N. Okay, so let's say Q to the D, small d. Okay, and by the simple results that I think you can prove this. This is a simple that that one can easily show that the dimension of K, the dimension of like D over L, right? So D over L times dimension of K over L is the dimension of K over D. Okay, so this is N, and this is as I define as D. Right? So that means that D must divide N. Okay. So now we can write, right? So D must divide N, and the D cannot contain N. D should not the same as N. Okay. So we have this, and we have yeah, D. So D should not the same as N. Right? Otherwise, that we prove our results. Right? So we should assume that D is not. Yeah, D is different from N. Okay, so now we can consider the class equation. Consider a class equation of the multiplicative group. Let's say D delete 0. Okay, so this guy is a multiplicative group. Okay, because every non-zero element has inverse, right? So this guy has Q to the N minus 1 number equals to Q minus 1. This is corresponding to like the centralizer, right? So this is K. And also some other things, right? Some other possible D or some other different class, right? So you Q D minus 1 and a Q N minus 1. Okay, so this is the class equation for this multiplicative group. Okay, so now let's do something, right? So we have this. Okay, so let me just write down. So we have Q to the D minus, so Q to N minus 1, Q minus 1 plus something, and Q D minus 1 for some D, and Q N minus 1. Okay, and then we know that Q N minus 1 is D N and phi D Q, right? This is the basic definition, the basic starting point. And then we also have so we can write this guy in terms of like phi and Q, right? And where C divides N and C less than N, phi CQ, right? We take out the largest part and the rest part, and then we do another, right? You get phi and Q is C divides D, and phi CQ, and where this is C divides N and C less than N, but C do not divide D. So we take another, this is called phi CQ, and this is phi N Q, right? Then we collect this, right? So this is the Q to the D minus 1, and this is the rest. So there are some rest here. Okay, so this equation tell you that the QD minus 1. Okay, so let me just say something. Oh, so this tell you that what? This tell you that your phi and q divides qn minus 1. This is simple, right? From here. And then we also know that phi and q will also divide this, right? Because I can cancel this qd minus 1 to the left hand side, right? So I can get qn minus 1, qd minus 1 equals to phi and q times other times something. Okay, so you have phi and q divides qn minus 1, qd minus 1. So that means that phi and q divides left hand side, also divides right hand side. So that means that phi and q must divide q minus 1. But from lemma, from the previous lemma, that we know that this phi and q, the absolute value or whatever is greater than q minus 1, right? Or basically we know that phi and q is greater than q minus 1 as n is q greater or equal to 2. So from here, you must divide. You must prove. You prove something, right? You prove what? You prove that oh, sorry, I'm stupid. Sorry, misleading. So this theorem also need to assume that n greater or equal to 2, right? I mean, because you have otherwise that this yeah, so otherwise that if n is 1, then only 1, right? If n is 1, then phi and q just q. Okay, so this guy is true only works for n greater or equal to 2 and q greater or equal to 2. Okay, so if here we have this, right? So this proves that n must be equals to 1. Because if n greater or equal to 2, and then also you can q greater or equal to 2, then this cannot happen. This cannot happen. Okay. So this phi and q divides q minus 1 must definitely give you n equals to minus 1. N equals to 1. Okay. So this is the, and if n is 1, then we prove these results. I will prove these results. Okay. See you guys next video. Hope you guys subscribe to my channel.